we named the Bionic Glove. So I will talk you through the motivation behind this research before going into the design of the device and how we characterized it. So upper limb prostheses have a very high rejection rate at about 1 in 3. And there are numerous factors for this, including the weight of the device and the lack of comfort. But another reason being the lack of sensory feedback. So in the human body, we have what is called the sensory motor loop. And this is a feedback loop which helps us to control our limbs. So what happens when we want to move our limb is we send signals from the brain through these motor neurons to the limb that we want to move. And then various receptors within this limb will send sensory signals back up to the brain through these sensory neurons. And this is a closed loop, which means that either pathway affects the other. When an amputation occurs, this loop gets broken, and it's thought that this is what contributes to phantom limb pain, which can be experienced in amputees, and it's an extreme pain that they experience in their missing limb. And it's thought that 60 to 80% of amputees will experience this, which is a huge proportion. So prosthetic devices currently focus on reinstating the motor part of this loop by creating devices that closely mimic the biological limb. However, I think it's also important to incorporate the sensory feedback pathway. And it has been shown that by doing so, this can reduce the phantom limb pain. It can increase control of the prosthetic device and consequently increase the acceptance rates. So I'll give you a quick overview of the device before going into more detail of the different components. So we have the pressure pads that sit underneath the fingertip of the prosthetic hand. And these contain a conductive liquid that gets forced through these channels as pressure is applied. And then higher up these channels, we have 2 electrodes, which are part of a circuit. And as the fluid reaches these electrodes, it bridges the gap between them and closes the circuit. And within this circuit, we have what are called shape memory alloy actuators, or SMAs, and these heat up as current gets drawn through them, and then they contract. And we have these SMAs incorporated into our tactile armband, which is worn on the user's skin. So down here we have our prototype of the device, and you can see the pressure pads, which would be incorporated into a glove worn over the prosthetic hand. We have our control unit, and then we have our tactile armband worn on the skin. So first of all, the pressure pads, they are made out of silicone, and we cast them in these 3D printed molds in 2 parts to make it easier to incorporate this cavity for the conductive liquid. We then silpoxy this together and roll it up to allow it to sit on the fingertip more easily. And we compared the sensitivities of 3 different geometries of this internal cavity, and we kept the volume consistent between these. So we had a rectangular, a square, and a circular cross section. And we measured the displacement of fluid with force, and from the graph you can see that the circular pressure pad was the most sensitive, as it displaced the most fluid with the least amount of force. And we think that this is because of the corners of the rectangle and the square increasing the tension across the pad as it's pressed, making it more difficult to displace the fluid. But as you can see that there's a large variance here, which means we need to do a lot more trials to before we can draw definitive conclusions. Secondly, we have our electrofluidic controller, and this is based on the soft matter computer that Martin and his team published in Science Robotics a couple of years ago. So we have the channels that come up here, and the 2 electrodes in each channel, which, as I mentioned earlier, would be wired up to the SMAs in the armband. Then we have our batteries, and this circuit board is only there to convert the DC current of the batteries into an AC current. And the reason for this being that we used saturated salt water as our conductive liquid. And if this gets exposed to a DC current, it electrolyzes, which generates bubbles. And these can get trapped in the channels and affect the connectivity at the electrodes. So in its simplest form, we would have one pressure pad connected to one set of electrodes, but we also generated a model for more complex computation and more complex tactile feedback, which is shown in this illustration down here. So here we have two pressure pads, which are connected to one channel. And this could be, for example, your index finger and your middle finger. And as one of these gets pressed, enough fluid displaces to bridge the gap between the first set of electrodes. And this would be our OR gate. Now, as both pads gets pressed, there's enough fluid displaced to bridge the gap between the electrodes higher up in the channel. And these electrodes can be wired up to different circuits, which can then provide different tactile sensations to the user to allow them to distinguish between one or two fingers having been pressed. Lastly, we have our tactile armband, which is based on the previous tactile device that we made. But it's basically a 3D printed armband, which is made up of 5 reentrant hexagon units arranged end to end. And across these units, we have our SMA actuators. At the bottom of the armband, we also added these tactile contact points that would allow the user to feel the sensations on their skin as the SMA contracts. And we did a user study to characterize this armband. Firstly, we wanted to determine the skin sensitivity threshold of participants. And this is at which point they start feeling the sensations on their skin. And we compared the 2 different sites on the arm. We had the upper arm and we had the forearm. And from our data set, we found that the forearm was maybe slightly more sensitive, but this was not significantly different following statistical analysis. Secondly, we wanted to determine the participants' abilities to identify different levels of pressure and different locations of actuation. So we set 3 different strengths of actuation, which was tailored to the participants' skin sensitivity threshold that we determined in the previous section. And we would actuate one of the SMAs randomly at one of these strengths and ask the participant to record which one they thought it was. So in our confusion matrix, we have the actual stimulation strength up here and then the recorded strength down here. And these values are in percentages. And you can see that participants found it quite difficult to distinguish between these different levels. And on average, they recorded 66% correct responses. For the location differentiation, we actuated one of the 5 SMAs at random and asked the participant to record which one they thought was actuated. Again, we have the actual site of actuation up here and then the recorded site down here. And you can see that participants found it easier to distinguish between the different location compared to the different strengths. And they had on average 81% correct responses. But you can see also from the confusion matrix that where they recorded an incorrect response, this was almost exclusively at the site next to the correct site. So to demonstrate the device in its entirety, we set up a proof of concept experiment. And here we had a 2-fingered robotic gripper, which had the pressure pads on them. And this was controlled by a user wearing the armband. And we set this up using the OR and gate logic that I demonstrated earlier. So we had the OR gate connected up to the SMA on the right here, and the AND gate connected to the SMA on the left. And the objective of the task was to grip the Rubik's Cube sufficiently to allow it to be picked up. And we had a screen in between the controller and the gripper so that the user had to rely solely on the sensations received from the tactile armband to perform this task. So in the first frame here, we had neither pressure pad engaged. Then as the fingers were moved closer together and made contact with the Rubik's Cube, both the OR and the AND gate were activated. And you can see here that this correlates to both of the SMAs contracting slightly. And then as one of the fingers gets moved away, only the OR gate remains activated. And so we managed to do this successfully and show the bionic glove in action. But we realized that this is just a proof of concept and we would need to do a full-scale user study to investigate the effectiveness of the device and the tactile response of the system on various objects. So in summary, the bionic glove is a tactile feedback device for upper limb prostheses. And this research really showcased the design of the device and its potential with a proof of concept. So we have shown that users can, to a certain degree, distinguish between different strengths and location of pressure, but there is scope for more complex computation. So obviously in the future, we would like to test this device in more real-life scenarios by using upper limb amputees as participants. And we hope that this device would allow them to be able to grasp objects more naturally and intuitively without the need for relying solely on their visual feedback. And as I explained earlier, if this is successful, then this could reduce phantom limb pain. It could increase embodiment and consequently increase the currently low acceptance rates. So thank you so much for listening. Please feel free to get in touch by email. My email address is just down the bottom here. Thank you.
Hi, I'm Greg, and I'm a fourth year FastScope student, and my research is entitled Intuitive and Immersive User Interfaces for the Teleoperation of Mobile Robots, with supervisors Emmanuel Giuliani and Paul Bremner. So imagine you're a nuclear robotics operator, tasked with going into a nuclear facility and potentially mapping it, or even retrieving an object from it that is to be sorted as radioactive waste. You're probably handed on your side as the operator something like we've got on the left side of the screen. So a joystick with the kind of camera feed from the robot displayed on the screen or laptop of some description. And just as a bit of context, on the right was meant to be a video of the kind of video feed you get back from the robot, which is very limiting. It's very extremely difficult to operate with this kind of equipment, and as a result, the operators tend to have to be trained for quite a long time to be able to operate successfully without causing errors. It's quite a stressful job, as you can imagine, as well. So the background of my PhD is to design and test an intuitive and effective user interface for the teleoperation of mobile manipulator robots. So trying to advance what we saw on the left, which has been the kind of status quo for the last probably 40 years. So just as a bit of context, the kind of robots I'm talking about, some of them are displayed here. So you have the mobility aspects, so some sort of wheeled robot or even legged robot, quadruped on the right there. and some sort of manipulator, so that could be an arm of some description. So what I'm looking into, one of the recent advancements in kind of user interfaces has been immersive user interfaces. So that's things like VR and AR headsets. And these things are just starting to be brought across to the world of robotics as well. So why might we favour these kind of interfaces? For one thing, they allow you to potentially look around your environment in a much more natural way. So here the user has the headset on their head, and perhaps when they turn their head, the viewpoint of the camera is also turned as well. So rather than having to manually turn it with another joystick, it offers a more natural and intuitive way of controlling the camera. Secondly, if you have things like stereo video feeds fed into the headset, you can get a better perception of depth. That's because the human eye is obviously being trained to use both of those sensors with your eyes to create the kind of depth that we all know. And finally, you've got things like tracked controllers, 6 degree of freedom track controllers, so that's position and orientation, which you can use to develop new control interfaces and potentially, hopefully, more effective ones. So yeah, that's about the interface. But what about the types of control we see? So on the most common, especially in fields like nuclear and other hazardous environments, you've got manual control. So this kind of robot has no autonomy. The operator will give it a command, say go forward with its joystick for 5 seconds, and it will just do that action exactly. So the operator is making all the decisions, and in fact they're involved in the lowest level control loop. So they'll see the image, decide what to do at that moment, and put the input then on the joystick to go to the robot. On the other end of the spectrum, you've got full autonomy. This is where the robot acts almost entirely without any input from the human operator. And in these cases, generally you require a full knowledge of the task beforehand so that you can program the behaviors that you want from the robot. So again, that full autonomy is great in some situations, but often we don't know exactly what we're looking for or how we're going to do it beforehand. So this kind of requires a lot of programming up front, which often isn't feasible. So in the middle, kind of grey area of shared autonomy. So this is where some autonomy is devolved to the robot, but you still have a human in the loop in some way. In the very lowest level of autonomy, it might just be the robot stops when it's very close to something. But there are also more kind of interesting ways that we can share autonomy between the operator and the human. If you think about the kind of mapping context that I've been given, you may not exactly know where you want to go at the beginning of the mapping task. You may want to visually inspect some things more than others. So having the ability for the human to control the higher level decisions is useful in a lot of these cases. So one of my ideas at the beginning of the PhD was, if we're teleoperating the robot using an immersive user interface, how can we kind of select the place that the robot's going to go to? What I got kind of inspiration from this VR gaming, where they have this method of moving around the environment called teleportation. Here's a quick video. So generally with the controller, which I say is tracked, you shoot out this little arc. It sets a position where it intersects the ground, and when you let go of the button, you automatically teleport there. So that was I thought that was quite cool, and I thought this could also be used as a way of selecting the waypoint for the robot. Obviously, you can't go there in an instant like you can in VR, but you could at least set that waypoint, and then the robot will go there autonomously. So again, with the shared autonomy kind of approach. So I set this up in simulation and basically tested it in a VR environment as a waypoint selection method. Here we can see this method with a 1 second delay between the operator and the robot. So simulating the kind of delays you might see due to communication and other things. So yeah, here the operator selects waypoints using the same method, confirms them using the controller, and then the robot goes there autonomously. So in comparison, we set up the VR user study to test this kind of method against manual control or direct control with two delay conditions. One where there was no delay between the user's input and the robot's action, and another condition where there was a second delay, as we just saw. And the operator was tasked with just moving through an environment from one end to the other, so avoiding obstacles and things like that. So the results were quite positive. We had a reduced task completion time, so that's the navigation task, especially where there was delay in the system. It's much more difficult to directly control the robot when there's delay, because the human basically has to account for the discrepancies between the movements. So task time reduced. The workload of the operator was also reduced because they're not having to do this kind of working out themselves. The robot's doing it. Usability was increased, again, especially in the delay condition. User preference overwhelmingly for the waypoint control. But finally, something we noticed was that there was quite a lot of VR sickness effects in that experiment. So here, as you can see, some people, three participants out of 37 had to drop out, but a lot of them actually said that they had some degree of VR sickness. So mitigating that's obviously an important factor. So now, since then, I've been implementing this kind of control in the real world, which has been interesting. I hope to have a video of this, but unfortunately I haven't quite pieced everything together. But yeah, so the setup I've got at the moment is a mobile robot that's actually moved from the Husky to a different mobile, slightly smaller mobile platform with a Z camera on top that does some of the spatial mapping on a pan tilt so the user can turn their head. So I've got a couple of upcoming studies to test the system. So anyone at the BRL, hopefully you'll be getting an email about these soon. The first one I'll be looking into the control mode, as I say, direct control versus waypoint control, and whether this has an effect on the level of VR sickness that people felt, because one of the outcomes of the VR study suggested that it might, although I didn't track it as stringently as I should have done. And secondly, we've got a couple of different types of camera that we want to test the levels of VR sickness as well. And so I think that's it from me. Thank you very much for listening.
Has anybody got any questions? No? Oh.
So you've been showing this of like a single user controlling a single robot. Do you think your methods would scale to be for an operator to be able to control multiple robots?
Yeah, that's a good question. The way I've kind of implemented it is first-person teleoperation, which obviously, I mean, you are adding in some autonomy. So the hope is that, yeah, you might actually be able to free the operator up to do multiple robots. But yeah, the way I've kind of implemented it lends itself primarily to one, because you're still doing quite frequent low-level control. But I mean, certain ways you can make this a kind of multi-robot thing, probably by separating the user from the actual viewpoint and having a 3D mapped environment, potentially real-time mapped, but or a priori mapped. That way, you can actually have an agent saying, "Oh, this robot go here, this robot go here," in the same sort of using the same sort of interface. So that's how I've pitched it, but probably won't get there in my PhD students.
Okay, we do have another question come in. Hi, Greg. Thanks for a great talk. Do you anticipate any major differences between how the users feel with a real robot compared to one in simulation? I.e., would users naturally feel more cautious?
That's a really good question. And actually, one of the things that I want to look into in this next set of user studies is trust. So how much the operator trusts the system to do what it says it's going to do, i.e. get from A to B. So that is a question I would expect them definitely to be more cautious with a real world robot than a virtual simulated robot. And if you add on to that a real world scenario where the operator is actually liable for kind of their job is to keep the robot from crashing into things, you've got so many more levels of kind of caution and potentially stress. So I would expect there to be a difference, and that's something that I'll actively look for.
Okay, thank you. Thanks very much. Thank you, Greg.
Thank you very much, everyone.
Thank you. Just need to stand that way. I can see the camera.
Hi everyone, so I'm Lizzie Stone. I'm a final year PhD student with the Tactile Robotics group. I'm going to talk to you today about walking on TacTip toes, a tactile sensing foot for walking robots. So human feet are very sensitive. You can feel what's underneath your feet, whether it be a nice fluffy carpet or a Lego brick. You can generally tell what is underneath your feet. But robots, in contrast, tend not to have tactile sensitive feet. If anything, they have a single four-stroke sensor which will give you a single data point on what is underneath your feet, which is nothing compared to the high resolution of the human foot. So humans are very good at moving through difficult terrains, such as balancing on beams, walking over rocks, or like in everyday life, walking up and down stairs. Robots, on the other hand, are not so great at these tasks yet. Imagine trying to get a robot to walk over terrain like this. Currently, very few robots would be able to do this, and they require extensive mapping and planning. So, if we then add in the complexities of the real world, there could even be darkness, such as at night, or there could be ground covering, such as leaves or snow, which makes it even harder for your vision or other ranged sensing systems to be able to actually tell what is going on the ground. So we will use a tactile foot to be able to feel what is underneath the robot's feet as it's walking, so that it can move into the real world and more difficult terrains. So what are the challenges of tactile feet? Why hasn't this been done before? So you need to a tactile sensor needs to be able to take the weight of the robot, but also be able to take unexpected impacts of a robot walking in difficult terrains. And a lot of previous sensors are quite fragile and can't take the repeated impacts. And then on the software side, it's quite high-dimensional data, so that needs to be interpreted, and the robot then needs to react appropriately to the simulation. So what was the hardware that I've been using? So this is the TacTip. It's a tactile sensor, which is a black dome with pins on the inside, and the pins got white tip. So when something touches the outside of the dome, the pins deflect, and you get these characteristic patterns. And you can use a camera above the pins to track the pins and see where they're going. So the main thing to notice is that there's a camera, there's an LED ring, and a detachable tip which you can take on and off. So this is the basis for the TacTip, which is the new design that I have. It is mostly the same. The casing is smaller and slimmer. The camera is a lot smaller than the original TacTip, so that it can go in a smaller minimal robot. It is all still be 3D printed and modular, so this means that you can update and upgrade different components of the sensor as you need to, or if they get damaged. So the thing that's missing from this design compared to the old one is an LED ring. So this was to light up the inside of the sensor. So I've removed this because it's too complicated to add in. The too complex design is likely to get damaged. So instead, I have painted the tips of the pins with a glow in the dark and phosphorescent paint. So here you can see a comparison between the two pins, the two types of pins. So the normal pins without an internal LED ring don't show up very easily against dark background. But with the glow in the dark pins, it's actually very, very bright and you can detect the pins quite easily. And you can even detect these pins across all sorts of light levels. So even in the pitch blackness here, because the pins glow in the dark, you can still detect them. So now we have a tactile foot. Here is the robot that I decided to use for initial tests. So it's a small insect-like robot with a static gait. So here we put the tactile foot on the robot. As you can see, it just replaces the end length of the original robot. So what was the task that I decided to do to test out whether a tactile foot would be useful for a walking robot? So my previous work was on tactile contour following. So this was following the edge of an object to see what kind of shape it was. So just following an edge. And so I thought, why can't we just do this, but with a tactile foot on a walking robot? So something analogous to walking along a pavement or walking along a beam. You can feel your feet whether you're going to fall off or not. So let's do this with the robot. Get to follow the edge to stay on a safe path. So there's two situations. One to follow an arrow path, and two to walk around a curved table. So the basic algorithm, if you want more details on this, go to my paper because it's too complicated to explain in a short talk. But it uses online learning. So at the start there is no model that's being trained. So it has to go and collect some data to train an initial model, which is this first picture. Once it's collected that data, it'll find the edge and then place its foot as safe distance from the edge. Having then moved on, take a few paces forward, it'll sense again, see where the edge is, and only use a single tap to try and find the edge. Using online learning, it's very efficient to learn where the edge will be. So here are the results. You can see the robot taking an initial set of data and then moving on, just tapping twice to see where the edge is, and then to confirm that this model is correct, and then moving on. It's using just the front right foot for now. It could use all four in future, that's preferable, so it can put all of its feet in the same location. But for now, for initial tests, we just decided to do one foot. As you can see, it makes it to the end of the beam without falling off. And it does walk around the table. So in conclusion, a tactile foot is very useful when traversing difficult terrain. Tactile edge following can prevent a robot from falling off raised paths. And online learning is very useful as it allows quick setup of models and transference between arms and legs. In further works, I'm looking at doing 3D contour following. So instead of just flat beams, beams that move up and down. Probably not as much as this bridge, but yeah. Other work could include other foothold selection methods, so where to place your foot in the boulder field, for example, or detection of different tactile feedback, such as slip, compliance, slopes, texture, and terrain classification. Further works, I will also be trying to put this on a larger robot dog. So the Hearts team at Wearable is making their own robot dog soon, which will be fun and exciting, and if you want to get in contact with them, their details are there. And thanks for listening to my talk.
Thanks. Has anyone got any questions? Lizzie?
So the tip at the moment is quite a soft fine rubber. Have you thought about how it can be made a bit more robust for longer term use?
Yeah, so the tip is filled with a gel, and that can be made stiffer. If that's what you mean. So if it's a stiffer gel, it'll less likely to get squashed and break between them.
Okay, yeah.
Anyone else? Thank you, Lizzie. Thank you.
Hi everyone, my name is Dominic and I'm working with Melanie and Ghobrial. I'm a PhD student in my first year of research and my project title is a ground-based web robot for the characterisation of nuclear environments. So, what is nuclear decommissioning? As nuclear plants are used, they are exposed to radiation and become radioactive. And nuclear waste also builds up in these plants. And in many of the early plants, it wasn't really considered what would happen at the end of their life, what would be done with this waste in the buildings. So this radioactive material, it poses a real hazard to people and to the environment. And this risk can potentially last hundreds or even thousands of years if not dealt with. So nuclear decommissioning is the process where these plants are dismantled and made safe to the point where they no longer require any protection for radiation. So at the moment, nuclear decommissioning is slow, it's hazardous, and it's costly. And there are some facilities that simply can't be decommissioned because they're too radioactive for humans to enter. So why use robotics? Has potential to lower the cost and access these facilities that humans can't, and generally make the process simpler. So Sellafield is a large nuclear site in Cumbria. It was commissioned in the 1950s, and it was actually the location of quite a big nuclear accident in 1957, the Windscale fire. And in Sellafield, a lot of the buildings are too radioactive to be decommissioned, too radioactive for people to enter, and they're only accessible by 125mm ducts. And what Sellafield would like to do is to go into these rooms and to capture data so they can gauge what's inside, how radioactive they are, and how they could be decommissioned. And the aim of my PhD is to design and build a robot to complete this characterization task. So the robot must fit through these ducts. It must be either small enough or must be able to fold to fit through 125mm duct. It must be able to capture this sensory data inside. And inside, there's the potential for the ground to be rough or uneven or for objects to be in the way. So it must have a way of getting over these obstacles, getting around. And what's key as well is it must not spread radioactive material, especially it must not take any radioactive material from inside and spread it outside the room. So I considered a few different morphologies. Quite an obvious one is a drone in a cage. A drone that could fly about, gather data, and if it were to bump into things, it wouldn't break. Downside of this is the downdraft spreads radioactive dust. So Sellafield don't want this. Tracked robots, they also have this downside where the tracks pick up radioactive material. It smears around the robot track mechanism and smears around the facility as well. The robots on the right are folding robots that have been designed to enter through ducts. So the top one is one that was used in the Fukushima plant, actually, designed by Hitachi. And in this is a tracked robot. In this certain situation, the smearing of radioactive material wasn't so important. The bottom right one is a robot designed in Manchester, and the downside of this is the locomotion mechanism. The Omni wheels really lack the ability to traverse over obstacles and rough terrain, so it's quite limited to very smooth environments. So I've been looking into wheel legs, whegged as a mechanism of getting around. So specifically morphing whegged, whegged that can turn from a wheel to a weg. And in fact, what I should have said is whegged are essentially legs that rotate around an axis. And they're really good for getting over obstacles. They allow the legs to so to speak, hook on to obstacles and to pull the ropes over the top. There are two types of morphing whegs. There are active and passive. Passive whegs are designed to change between the wheels and legs passively when certain conditions are encountered, or when the robot is driven in certain ways. And active whegs, they are directly mechanically controlled, so those can be opened and closed at will. So I've decided to use actively controlled whegs, as I think it just offers a lot more functionality and a greater degree of control. So this is the concept I've designed. It folds between the two states seen here. So the closed state is on the left, and this closed state allows the robot to be pushed through the small duct. On the other side, it can then open out into this open shape. So the tail opens out, which allows forward movements, and the sensor platform opens up, which then allows the sensory data to be captured. The whegs can either be in open or closed position. They can act as wheels, which are great for moving around on flat surfaces, great for accurate odometry, or open in the weg position, which is really good for getting over the obstacles. This is the prototype I've been working on. So this is the first prototype. So it's quite a basic one. The whegs are actuated through using a wire that goes into the weg mechanism and can pull the legs out, the blades out. And this wire is connected to a swivel, which allows full rotation without any tangling. So it's a basic. The control's fairly basic. It's a stepper motor to actuate the legs, DC motors to control the movements of the wheels, and it's just powered by a tether. So unfortunately, I was really hoping to have video. Not quite able to get that today. I'm told this is quite normal for a PhD. So future work, I'd like to test this current prototype and hopefully write that up, get some good data on that. Further prototypes. So I'd like to build in the sensors. I'd like to get a more robust way of actuating the whegs. I think the current mechanism, while it's great for a prototype, it needs work to be more robust and a bit more useful. And I'd like to include the tail actuation as well, which isn't on the first prototype. So I'd like to look into some teleoperation, potentially with VR, and eventually include some autonomy as well. And look into as well the mix between the autonomy and teleoperation and the switch between the two. And finally, I'd like to carry out some user studies and see how people react to the robot. Thanks for listening. Any questions? So essentially, without the tail, when the legs are rotated, the body would just spin. So the tail essentially prevents that and allows the forward motion. Yeah.
So do you have any idea how much kind of this will improve the ability of the robot to traverse terrain?
Yeah, so essentially, a wheel with, if you imagine that sort of very good frictional qualities, could only ever overcome an obstacle that's about half its diameter. And in reality, it's actually quite a lot less than that because the wheel's likely just to slip. Whereas a weg can grab, depending on its shape, can hook onto an object that's the same diameter as the weg. And considering the limited diameter of the duct as well, and the fact that the weg can fold out to a larger diameter, compared to a wheel, it's quite a large increase. Yeah.
So just watching Lizzie's talk beforehand, did you consider legged or
I did, and I realised I hadn't put that on the slide actually. So the reason I decided against that is essentially the complexity for this kind of environment and to carry out this very practical near-term task. I decided on something that's just very reliable, and I think wegs have that advantage over legs at the moment. And sealing as well is much easier with something like this, which is important for nuclear environments.
Thank you.
Thanks.
Hi, hello. My name is Joe. Apologies, I can't be here physically today. If you've been here earlier, you might have seen Severin's talk about a project about a robot in a school for autistic children. That is where I am currently collecting data for that study. So apologies for not being here. But when I'm not doing that, I am working on this, which is robots in need. How can robots get assistance from humans in situations where they require assistance? And yeah, so my research kind of focuses on this idea primarily because no matter how kind of amazing we make these robots and how many situations we think we can prepare for, the real world is really messy, and so there are going to be inevitable situations where robots, just either because of limitations in programming or their physical limitations, aren't going to be able to deal with the situation. So robots kind of need strategies for being able to get assistance from humans. Similarly, any robot that's designed to collaborate with a human, whether this could be like in a factory line or something like this, it's useful for them to be able to get that assistance from humans so that they can collaborate, complete whatever task they need to complete, and kind of work together. So my work kind of looks at this idea primarily from this perspective of emotion. So looking at the role of emotion in motivating helping behavior. And it kind of builds on this idea from psychology of kind of empathy and empathizing with other people's emotions to kind of motivate helping. So this is a super simplified diagram. The reality is way more complicated. There are loads of processes kind of happening, but to simplify down to this extent, basically we're looking at this idea of in human-human interaction, if somebody needs assistance, either consciously or otherwise, they are expressing an emotion. Often this is going to be a negative emotion, possibly like sadness or something like this, where somebody else seeing that shares in that emotion in this process of empathy, and that's thought to be quite a big motivator for helping between humans. And if that help has been successful, then at the end of it, everybody feels good, everybody feels happy. The helper feels good about having helped somebody in a phenomenon that's kind of known as helper's high. So at every stage, kind of emotion is kind of important for humans helping other humans. So my research kind of takes this idea and explores whether this kind of interaction can also happen for interactions between humans and robots. So at the very start of my PhD, I explored this idea with a Miro robot, this little zoomorphic robot, and we had a situation where basically the robot wants to try and get at these little tennis balls in the corner, and when it gets stuck, it kind of expresses different patterns of behavior, So we have like one condition where it's like completely neutral throughout, one situation where when it gets stuck, it looks really sad. And then once it's received help from a human to get those tennis balls, it returns to a neutral behavior. And then we have the final condition where it's sort of neutral while it's stuck, but then once it's helped, it expresses this kind of happy behavior. And when we're sort of looking at this, we find that there is actually a kind of subtle effect of emotion in that when in these emotion kind of conditions, and people kind of repeated this interaction a couple of times, people responded a little bit quicker when the robot showed these kind of emotional behaviors. And this was particularly true, interestingly, for people that are high in dispositional empathy, so kind of empathy as a personality trait. We noticed that those people that are high in empathy tended to respond quicker when the robot was showing like sad behavior. So there's already this kind of complex kind of interplay between like emotion and the person that's interacting with them, with the robot individually. So then we started to explore slightly more complex or more varied patterns of emotional behavior. So in our next kind of experiments, and these were online experiments where we looked at how people responded, whether they said they would be more or less likely to help a robot across every possible kind of combination of neutral, sad, and happy behaviors. And we were particularly interested in looking at what happens for unusual patterns of behavior, because normally when you need help, you're not really happy about it. So in this sort of unusual pattern of behavior, we're kind of intrigued to see whether people would be more curious about this, whether that unusual pattern would kind of encourage more interaction with the robot. And the answer turned out to be yes, but not for the reason that we thought. So we explored this with the Mirror robot and the Now robot. You may notice a slight difference in background. One of these was carried out before the pandemic, one was carried out after the pandemic. Fortunately, some of our furniture matched the lab, so it worked out pretty well. But interestingly, for the Mirror robot over here, people tended to actually recontextualize this happy behavior. So they tended to interpret it as being more like agitated, so it's kind of looking around and wagging its tail. And people were interpreting that as agitation, and so people were responding saying that they would be more likely to help it in that situation. So it turned out that this kind of happy behavior, it did help, but not in the way that we were expecting. Whereas conversely, the Now robot, people seem to be better at interpreting its behavior sort of as intended, as they tended to perceive it still as relatively positive, even though it was kind of like stuck. So there's also this really kind of complex interplay between emotion and the robot's form, and again, like people's willingness to help the robot. And so we kind of wanted to explore also more long-term interactions, but going back to a slightly more simplified situation. And so in our sort of final experiment, was again in lockdown. We wanted to look at this idea of help as high, and whether people feel good about interacting with the robot and what role this might have in influencing further interactions with the robot. So we had a setup where the robot would basically stay with people for a week, for 4 days, and over that time it would act kind of like a companion, and would occasionally ask for little interactions with the participants. And on 2 of the days it was completely neutral, it didn't really have any emotion behavior at all. And on the last 2 days it had slight alterations in the way that it sort of spoke to participants and the way it behaved, so it had a little bit more emotion to it. Interestingly, with this one, the pattern of emotion versus non-emotional behavior didn't really have a huge impact, or at least no statistically significant ones. And the thing that we did notice, though, was that across the board, people did feel good about helping a robot. And so in their sort of self-reported moods before and after the sessions interacting with the robot, people were consistently rating their mood higher, or more positive emotion, after interacting with the robot compared to before the interaction. And this was also verified in interviews with participants who sort of verbally said, like, it feels good to help a robot, and like they've helped it and had that kind of positive interaction with it. So yeah, it was, although the emotion itself didn't have a huge, or the emotional behavior of the robot didn't have a huge impact, we did notice a big kind of influence on people's emotion. And so this kind of brings us a little bit to our sort of final kind of question, which is looking at this idea of ethics. So we've seen already that emotion has a huge role to play in these kind of interactions, but since emotions aren't actually experienced by robots, we kind of wanted to know whether that's actually ethically acceptable for robots to use emotion either to gain assistance and potentially to have this kind of knock-on effect on people's emotions, given that it is basically emotionally manipulating people into interacting with it. So in this experiment, again, we compared the Miro robot and the Now robot. And we also looked at two different contexts. So one of the big concerns in ethics, you may have heard this in some of the other talks, is about using assistive robots with potentially vulnerable populations and the sort of ethical acceptability of using emotion to deceive these kind of vulnerable populations. And so in this experiment, we kind of introduced the robots as either assistive robots or purely companion robots, to see what kind of influence this had on their opinions of the robot's emotional versus neutral behavior. And what was really interesting was that across the board, regardless of whether it was neutral or emotional, people rated it as ethically acceptable. And there was a slight effect of emotion that was rated slightly less ethically acceptable compared to purely neutral behavior. But yeah, overall, people were rating it pretty positively. And this has like some big implications for sort of how we go about deploying these robots, because as robots become more common, we need to think about what kind of impact they are going to have on people, and responsible use of emotion and robots in general. It is this really big area, and this is sort of a tiny sort of tip of that iceberg, sort of looking at this question. But it is really important to be kind of looking at this in general. So yeah, that is the kind of very broad summary of everything that I've kind of been looking at in these past few years. If any of that is interesting to you, or you have any questions about it, I'm always very happy to talk about my work. So please do send me an email at Joe Daly's at brl.ac.uk, or on Twitter, where I occasionally tweet things. Yeah, thank you so much for listening, everyone. Have a great rest of the conference, and goodbye for now.
Hello everyone, I'm Liam. I'm a third year FastScript student, and I'm going to present my work on learning dynamic flight manoeuvres for agile uncrewed aerial vehicles. This is work that is supported by the Defence Science and Technology Laboratory. So a quick word that I am a part of the Bristol Flight Lab, which is the University of Bristol's Centre for Multidisciplinary Aerial Robotics Research. So that's across a number of different topics, different areas, including design and control of fixed-wing vehicles, of multi-rotor vehicles, of bio-inspired aircraft. Also recently got into a lot of kind of machine learning for flight control, which is my topic. And then another large part of what we do is kind of field operations, so working in collaboration with other departments in the university, working with other universities and different organisations, conducting things like volcanology, meteorology, and radiation sensing in Chernobyl, all that kind of stuff. So you should check out our website, Google Bristol Robotics Lab. You'll see us online and see what the kind of cool stuff we're into. But now more about my research. So my research is about using machine learning techniques to increase the agility and maneuverability of fixed wing aerial vehicles. So why do we want to do that? So fixed wing vehicles, like a plane, has a number of advantages over a multi-rotor like this multi-rotor here shown in the picture. A fixed wing vehicle tends to have much kind of longer range and higher flight endurance compared to a multi-rotor, but it has some very significant disadvantages, and that usually it's far less maneuverable, and so it's difficult for it to conduct agile obstacle avoidance. Usually requires a lot of space for landing and takeoff. So this is sort of the kind of thing that we're trying to fix, essentially to make a fixed wing vehicle have some of the characteristics of a multi-rotor. And the main kind of use case for this is being able to use fixed wing vehicles in urban environments. So that we can have some of those advantages, such as the longer flight time, while still being able to avoid obstacles, quickly navigate in kind of tight spaces that currently only a multi-rotor could really do. And so some of the kind of applications you see for this are sort of remote sensing and surveillance, using kind of cameras and sensors deployed on the vehicle, rapid delivery and resupply. If you have kind of need to get packages to an area quickly, you use a fixed wing vehicle to deploy small packages very fast. And of course, like all robotics, search and rescue is another possible application. So the kind of branch of machine learning that I use is called reinforcement learning. So reinforcement learning is all basically about learning from trial and error. So you basically try and do a task, and based on how well you do that task, you receive a reward, or the agent receives a reward, and it uses that reward signal to update, in this case, a neural network. So you are aiming basically to identify a policy that will maximize the reward and perform best at that task. Reinforcement learning now has been around for a while, but modern implementations have kind of made it particularly useful. Use neural networks, and the kind of the merging of reinforcement learning with deep learning have allowed it to kind of be useful for complex tasks. And in my work so far, it's all about the key kind of aspect of my research is reinforcement learning that's useful in the real world. So kind of stepping beyond simulation and taking it into the real world. So testing everything on actual platforms and seeing how well they do. So a quick thing about reinforcement learning, if you don't know already, it's been quite a an area of rich research recently, past past decade, shall we say, really kind of intense research from a large number of organisations that see the potential for this technology, and a lot of that has been kind of simulated tasks or video games, but in recent years, well, we've kind of seen it applied to kind of real world robotics tasks, both kind of dexterous manipulation, walking robots, so learning controllers for quadrupedal locomotion, and as well as there's been applications of it for kind of aero robotics applications, such as this attitude control for a quadcopter at the top here. So this kind of next slide will show you a quick example of what I mean by reinforcement learning. A very simple example of this is a plane trying to learn how to do a loop in simulation. So you can kind of see at the start where on the right hand side it's kind of doing random actions and is not doing a loop. It's not doing very well at all. It's on the sticks, simulated kind of actions. It's just randomly moving and trying to learn what the actions do. And after 5 hours of training, it kind of knows what it should be doing and has learned how to do a loop properly. And it's kind of much more considered and knows what actions it should be performing. It's a very simple example of kind of what RL is in this kind of context. So my kind of focus so far has been this kind of perched landing maneuver, where the objective is for an aircraft to land safely on a target position, whilst also reducing the kind of required landing distance. So that you don't need sort of a long runway for the aircraft to land. You also don't need any kind of rescue equipment like nets or cables to try and catch the drone when it lands. So then in this kind of example here, it's showing landing on the back of a ship, but it could be landing in any kind of small tight area where you don't have a lot of space for the aircraft to land. And this kind of perch landing maneuver is kind of inspired by the way that some birds land on the ground. So they kind of use their wings and throw them forward to perform a kind of perched, flared landing. So at the bottom left here, you kind of see our kind of custom variable sweep aircraft with a kind of off-the-shelf model aircraft which has been modified to add these kind of sweep wings, so it can sweep its wings backwards and forwards during flight to kind of generate these pitching moments and generate this kind of perch landing. And in my kind of work at the moment, I'm looking to train all this in simulation. So I have kind of a model of the aircraft that's generated from mostly wind tunnel data, and that's to create a kind of simulator for the aircraft. And then I train manoeuvres in simulation with different conditions, such as different start velocities, different attitudes, different wind conditions, both kind of steady state and gusts, and trying to kind of generate robust controllers that can deal with a wide range of conditions. And then these are all trained on the University of Bristol's high performance cluster for about 40 million episodes, which is about 100 hours of training. And then once it's trained, I evaluate it in simulation, and the ones that perform the best, I then test in the real world. So I then have an aircraft which has kind of hardware on it to be able to kind of take the simulated models and fly in the real world. So kind of this kind of array of sensors and actuators and computation that have kind of been installed in the modified aircraft. So, so we have a flight controller which gets the kind of state and controls the aircraft during most of the flight, a Raspberry Pi which runs the neural networks and sends the actions to the flight controller, and then a suite of sensors such as GPS and a magnetometer for positioning and attitude, and an airspeed sensor so the aircraft knows how fast it's going. And then once that's all done, we've got an aircraft, we train them, we then go and fly them. So this is kind of flying at the Fenwood Farm flight test facility for the University of Bristol. And these in this video here, you see these baseline controllers that aren't doing particularly well, because these are the baseline, and these are ones where I was kind of testing against, where they have the least robust controllers. Then these second models here have kind of the medium robustness, if you want, and have some kind of randomization during training. And these are kind of perform better using the sweep wings to kind of extend the flight. And then these kind of third set of flights are the most kind of robust models of this particular flight test, and they know what to do when they face certain flight conditions, and use the kind of the wing sweep and the elevator to maintain the kind of attitude of the aircraft and try and reach its target position. And of course, in this case, they're all flying at altitude because I'm scared about actually landing it on the ground, so I kind of simulate it 50 meters above, so it's not actually going to crash if something goes wrong. And it's just a quick plot of some of that data. So this is kind of, you can see here what basically the vehicle is trying to achieve here, where we have a start position of 40 meters away from the target position, and it's trying to get to 0 meters, which is the target position of the landing. And on these particular models, it does okay. It gets about 5 meters short, but I think this is more just due down to physics and the vehicle facing higher kind of wind speeds that it could possibly deal with. So that's kind of one limitation of this maneuver, is that the vehicle doesn't have throttle control when it's doing it, and so it only has the energy it has at the start of the maneuver. But you can also see here the actions that the reinforcement learning agent has chosen. So you can see the wing sweep and the elevator control in the middle plots, and then a couple of the other kind of longitudinal parameters, sort of the pitch angle and the pitch rate on the top there. So that's kind of what I was working on. My work now is kind of progressing that to more complex and more interesting problems, with kind of a new aircraft. So moving beyond the sweep wing Bixler kind of glider there, moving to a much more high performance aerobatic aircraft with very kind of high thrust, much larger control surfaces, so you can do much more interesting manoeuvres. And then also looking to go beyond and do some kind of proper 3D flight manoeuvres that could be useful in a in the urban context. So agile gate navigation in this case would be something similar to like the Red Bull air racing or drone racing you might see with quadcopters, but instead doing this with a fixed wing aircraft. And this would possibly be useful if you were trying to navigate tight spaces in a kind of urban setting. Rapid descent and landing. So this case is kind of similar-ish to what the perch landing was, where you're trying to basically get from a height down to the ground. This would be kind of probably a much more dynamic maneuver using much more of the thrust of the aircraft to try and achieve this. And it wouldn't necessarily have to be for landing. You could use it just to try and go from a height, possibly ducking down in between buildings and then flying on afterwards. And then the third possible maneuver I'm looking at is agile obstacle avoidance. So in this case, the idea is that the vehicle kind of suddenly has an obstacle that jumps out in front of it, such as possibly another aircraft or a bird, or even something that it detects late. So it might be difficult for the sensors on the aircraft to detect, such as a cable or a wire. And then it has to perform an agile maneuver to try and avoid it. And I was looking to use reinforcement learning techniques to generate flight controllers to try and perform these maneuvers with my new aircraft, which I've kind of been working on and building at the moment. And for my final slide, I'll give you my colleague Tom, who's the British champion of model aircraft flight. He is here flying my new aircraft around Fenswood Farm. So this is all manual control, but I'm hoping to do some automated testing with this soon. But yeah, so if you have any questions, you can watch this nice video of my plane flying around the sky.
Thank you, Liam. Has anyone got any questions for Liam?
Yeah.
So now are you using this model without any wing sweep actuation?
Yeah, so we've kind of moved to a more conventional aircraft design for this one. So it has no sort of actuation currently. Instead, we're kind of relying on the kind of conventional performance of the aircraft and the kind of the control surfaces and the thrust that it has available to do things like this, to be able to do the kind of dynamic maneuvers. But it is possible in the future, maybe not for me, but beyond other PhDs that we might look to do, adding some kind of more interesting actuation to the platform, such as sweep wings or twist wings or morphing wings and all that kind of stuff.
Do you do any sort of online retraining of the models, or do you just take them straight from the simulation and plug them in?
So that's currently the way it's done. It's all in simulation and then tested in the real world. Online refinement or generation of models is something I'm currently looking into for this new aircraft. It's something I'm exploring and would like to use. I think it'd be quite useful, especially because it's quite a challenge to get a kind of very high fidelity model of an aircraft like this, even from just wind tunnel data. It's very difficult to try and do that. So I might look into using sort of online learning of models to overcome some of those barriers.
I have a chat question. Okay, is it possible that using the trained control from the simulation environment to the real world UAV control?
That's that again.
Ming,
Yeah.
is it possible that using the trained control from the simulation environment to the real world UAV control? Is that the same?
Yeah,
kind
so
of?
I guess one of the things I'd cover here is kind of the reality gap is kind of the reality gap between simulation and the real world is one of the kind of the key challenges of trying to use these reinforcement techniques or even other kind of model predictive control techniques. Trying to use them when you're moving from simulation to the real world. It's a significant challenge, and it's something that I overcome using a technique currently called domain randomization, where you try and add a lot of variants of kind of dynamic parameters in the simulator. So parameters that you may not be quite sure of or might not be correct in your simulation, and you try and add them in during training to add a bit of randomization. And hopefully you will kind of generate a neural network that is robust enough and has enough kind of experience of a variety of parameters that it is kind of close to what the real world actually is. But you know, fixed wing flight is a significant challenge, especially when you come into like very dynamic, non-linear post-stall maneuvers where you've got a significant amount of non-linear of non-linear conditions of turbulence, and yeah, that transfer between simulation to reality is a challenge that is difficult to overcome, and that's why, yeah, and it's kind of a large focus of my work is trying to bridge that reality gap.
Thank you, Liam.
Forgive me if this was mentioned, but is there any closed loop control using sensory data on the aircraft, or is it just applying the learned algorithms directly and assuming it goes well?
So the way mine currently works is that, yeah, the neural network is deployed on the Raspberry Pi, and the state from the aircraft, so its velocity and everything that's taken from the flight controller, is fed into the neural network as kind of as the state, and the neural network will then give off the actions, which are the rates of change for the elevator and the sweep angle, and they are then converted and sent back to the flight controller. So it's kind of, we call it kind of closed loop reinforcement learning control. There is no sort of like abstraction layer between what the action from the neural network is, and then it's directly sent to the aircraft and used there. Kind of when I inherited this work previously, it was kind of a bit more, there was a lot more of a kind of abstraction between what the reinforcement learning said and what was actually kind of done on the vehicle. There was more of a conventional PID control going on. But in this case, it's kind of direct state to action kind of thing going on here.
Great. That's everything. Thank you, Liam.
Morning, everyone. Autonomous systems are being developed to operate in infinite demanding environments where they need to continuously learn and adapt and familiarize themselves with new instances or new tasks. But the question is really, how do we ensure that this continuous learning is done in a reliable way, in a way that does not affect, at least negatively, the existing performance of the autonomous system? I'm Abanoub Ghobrial, a PhD student funded by Thales at the Trustworthy Systems Lab at University of Bristol. So let's say we have an autonomous system, which is a robot in this case, and its job is to classify or group together circles of the same color. And let's say at deployment time, it was really good at grouping together yellow circles, but not so good at grouping black and red circles. Over time, it can either improve or worsen. It can become better at grouping these circles together and also group really well black and red circles, or it can worsen. It can become worse even at the task that it was already good at doing when it was deployed. So with autonomous systems, there are really no guarantees on what's going to happen in the future. We want the desirable behavior. We want, the whole point of making a system autonomous is that we want it to improve. We don't want it to worsen. So we want it to go towards the desirable behavior, not towards the undesirable behavior. So what we want really is we want to get rid of these question marks, which is we don't want to give it a chance to improve or worsen. So we effectively we want to put a filter where it stops the system from worsening but allows it to improve. But how do we achieve that? Let's look at the challenges first. How do we detect? So the first challenge is how to detect undesirable behaviors. In other words, how do we tell the system whether it's improving or worsening? Now, I've put the words improving and worsening there because I know what the system is meant to do, and I know what's right and wrong. But how would the autonomous system know? We want to give it this capability of knowing whether it's actually doing any better or any worse. So one of the techniques that I'm looking at in my PhD is by using indicators. So we want to let the autonomous system know it's doing better or worse through using key performance indicators or safety performance indicators to make it improve its operation. Sorry, to make it detect whether it's doing better or worse. And one of the things that I'm looking at in collaboration with the Connected Autonomous Vehicles group at the BRL is the conversion of standards descriptions into indicators. So how do we infer or get indicators that can continuously monitor an autonomous system through inferring things from standards. So, for example, you can have an indicator that continuously monitors the distance of an autonomous vehicle from other vehicles around it, or of a self-driving car, in other words, to other vehicles around it, and hence infer whether it's violating any rules or so. Another method that I'm looking at in my PhD is cross-referencing. So let's say we want to have a system that classifies where or identifies where a human is in a picture. Now, you can do that just by using the body features, the body shape. We can have a trained model that just looks for that, and it will give us a good idea, but it might do mistakes as well. Like here, like you can see in the picture here, my hand got identified as an independent person. So instead of just using one trained model, we really want to use several independently developed systems or models that do the same thing but in different approaches, or in different ways, or developed in different ways. So let's say you have another trained model that looks for facial features, and we have another trained model that looks for limbs or something like this, or fingers, and so on. And grouping these together, we can compare and generate a verdict of what's expected from unexpected, and hence what's improving and what's worsening. The other challenge is regarding forgetting. Now, many of the autonomous systems, if not all, have neural networks in them, and a typical feature of neural networks is that when they're trained on new data, they forget. They tend to forget what they've been taught before, or the previous training on previous data sets. So what we want really is to maintain at least the desirable behaviors that we used to have. So we don't want the system after deployment to get any worse. It doesn't necessarily, if it doesn't improve, at least it has to stay the same. i.e., in this case, just maintain the ability to identify yellow circles properly. And for that, we're looking at techniques that can protect weights and biases in neural networks, which here are resembled by theta. And what we want is to be able to at least conserve or put a penalty during training so that the system goes towards an intersection where it's both good at doing the old task, or the old is good at doing its old tasks, and also good at doing the new tasks that it learned. So that's another thing that I'm looking at, which is how can we generate these penalties, or just generate these penalties. So summing all of this up, this all can be put together in the context of autonomic computing. Now, autonomic computing is quite popular in data clusters and networks, and it really consists of a managed element and an autonomic manager. Now, the managed element is really the system that we want to monitor. That the system, in this case, the autonomous system, or in our earlier cases, the robot that classifies the yellow and it classifies or groups together circles of the same color. And the autonomic manager tries to monitor and analyze the system continuously to identify what's good and bad, and then accordingly plan and execute an action. And this is really what I've covered earlier today, which is you can use the orange square here resembles the first challenge, which is trying to identify what's right from wrong, trying to make the system, or the autonomous system, identify by itself what's right from wrong. And the other part, which is to try and at least maintain what we have whilst we are learning the new tasks. That brings us to the end of this talk. Thanks a lot. And if you have any questions, please feel free to email me or Kirsten, either my supervisor. Thank you.